So this is the first problem of today's Div2 contest. In this problem, we are given that Philip has a row of cells, some of which are blocked and some are empty. Now he wants all empty cells to have water in them, and he has two actions at his disposal. The first action is place water in an empty cell, and the second is to remove water from a cell and place it in any other empty cell. Now, if at some moment cell I, which is I is between 2 and n minus 1, is empty and both cells I minus 1 and I plus 1 contain water, then it becomes filled with water. Now we have to find the minimum number of times Philippe has to perform the operation of first type, and we don't have to minimize any of the operation. Like we don't have to minimize the second number of operation. Let me. So this is a very simple problem. The only thing we need to there is just a small observation that the water, if I minus 1 and I plus 1 are having water, then the ith cell will also contain water, right? So first of all, let me write this down here. If two cells are having water, then this cell will also have water, maybe after some instance. So what we can do, we can, like using second type of operation, we can always pick up this and place it anywhere. And after, why we can do this? Because eventually after, if even if we remove this from here, it will again get filled, this cell. So the only thing, when we cannot do this kind of thing, when let's say this is blocked and this is blocked. So now we cannot have this kind of arrangement, that is have two cells with water, and each time this middle cell gets filled, we'll keep it somewhere else. We'll move this water to some other cell. But here this kind of thing is not possible because we don't have three cells in a row which are empty. So in this case, we'll have to fill all of these cells. Like Philip will have to fill all of these cells one by one. So answer is nothing but the count of empty cells in this. Otherwise, if we have at least the count of cells empty, maximum number of count of cells that are empty is more than or equals to 3, then our answer is simply 2. Otherwise, our answer is count of empty cells. Is it clear? Yes, no?
Yes.
So let me show you the implementation. So this is the implementation. In this, I have just counted how many cells in a row are empty and continuously are empty, and I'm inserting them in my count vector. So if I don't have to, okay, I'm sorting it, but you don't have to sort it. You can find maximum directly also. And I'm inserting 0 here just for the sake that I can sort it, and it's possible that none of the cells were empty. So I'm just checking if the maximum value after sorting, the last value will be maximum. If this is less than or equals to 3, I'm printing the sum. Otherwise, I'm printing 2. So hopefully this is clear.
Yes.
So, okay, let's go to the next problem. So in this problem, we are given that there are numbers 1, 2, 3 written, like a number with digits 1, 2, 3 written on the board. And so after having these digits written down, what we can do in one operation, we can choose 2 digits and remove them and write the third digit, which was none of these. I'll explain it here. Suppose there are some digits 1, 2, and 3 written on the board. So what we can do in one operation, we can choose 2 distinct digits, 2 different digits, remove them, and write the third one, whichever we didn't choose. 1 was chosen and 2 was chosen. Digit 3 was not chosen. So we'll write this 3 on the board. So we just have to find whether or not it's possible that after some operations only digit 1 is on the board, digit 2 is on the board, or digit 3 is on the board. So for all of these 3, we have to check. So this is just simple implementation. What we can do, see, each time when we are removing some digits, 1 or 2, let's say these are digits 1, these are digit 2s, and this is digit 3. So when we are removing some digit, see, first of all, if I have to check for 1, so the minimum number of times of these two, 2 and 3, those can easily be removed, basically this part, and 1 will be written down here. Now if the remaining digits is even, the answer is possible. Otherwise, like, we'll have to find the minimum. Otherwise, if it is odd, the answer is always not possible. Why? Because see, even if, see, first of all, you'll choose some these two, and like after removing one digit from here, some this digit will always get added. Now what you can do, you can choose these two and again remove these two, and you'll get this one back. But now what will you do? Eventually you'll be left with something like this. There is only 1 2 left. So 1 2, you remove these two, you'll get a 3, and you have no choice, right? You'll do 1 3, you'll this 2 will appear back. So that's why if after removing the minimum number of digits from 2 and 3, if the remaining digits in this or whatever is 2 or 3 is odd, the answer is not possible. Otherwise, the answer is always possible. And how is it always possible? Like, let's say 2 was appearing 2 times here. The remaining digit was 2. So first you choose these two. Okay, this one was not there. So you choose these two digits, and like, you just need to make sure that one is at least, like, the count of one is at least, like, the digit one is at least once on the board. And to this, like, you'll also add to the count one, you'll also add this one, like, one time. Why? Because this is the number of times that you have already removed these 2 and 3 as a pair. So let's say this is min count of 2 3. So first of all, remove this. To count of 1, add minimum count of 2 3. Now this is the total count of 1. After this, if total count of 1 is more than 1, then the answer is always possible. Why? Because you'll choose this one and this 2, you'll remove these two, and you'll get 3. Then you'll choose these two, and this one will come back. So you can see that we are removing these twos in pairs, right? So that's like the solution. You just have to, for like, I have done this for 1, we can do this exactly for 2 and 3. So let me quickly recap, like, just, so first remove the minimum number of digits which are in 2 and 3. Then just check if the remaining count is odd. The answer is no. Otherwise, the answer is always yes. If even, then the answer is yes if total count of 1 is more than 0. Otherwise, if this is not true, this is not true, then the answer is 0. Because what will happen, that there is no 1, there is only this 2 left. Maybe even if it's occurring even times, you cannot remove it, because you'll have to choose 2 distinct digits. So whatever we have done assuming that we are finding answer for 1. We can do exactly same thing for 2 and exactly same thing for 3. Is it clear?
Yes, it's clear.
Okay. So the solution is here. So first I'm taking A, B, C as input, then X, Y, Z are just some temporary variables. So initially X is A, Y is B, Z is C. I'm finding minimum of Y and Z, that is nothing but B and C. I'm subtracting it from Y and Z and adding it in X. So this is my first digit, and these are 2 and 3, digit 2 and 3. Then if the why I'm doing maximum, because one of them will be 0 now, Y and Z. Out of these two, one will be 0 and one can be non-zero. So whatever is left, if it is, the remaining is now odd number of times written on the board. The answer is simply, it's not possible, printing 0. Otherwise, if X is at least, this is the X, right? The number of times first digit is appearing on the board. If it is more than 0, so I've just written if X, then print 1, otherwise print 0. So I have done the same thing for other two cases also. In this, X is B. So I'm finding answer for X, right? So X is B, and in this case, X is C. And the rest of the logic is exactly same. So is it clear?
Yes, it's clear.
Okay. So going to the third
You
problem.
have,
Yes,
hello?
yes,
Can you show the code again?
yes. Here it is.
Okay. I'm actually a bit confused. Like the code is actually divided into different blocks, right?
Yes, yes, yes.
So
Like,
all the statements will get executed.
yes. Like there is no if else. Like this is
Got it,
just,
got it.
this will just simply flow. You can add an extra, like this kind of thing. It don't, the, like it will get completely executed. If I have if else blocks, then either this part get executed or the else part gets executed.
Got it. Got it.
Like, usually why I did this, because see, if I declare a variable inside here, like forget about variables also. This is just a cleaner way to write. Like this part has nothing to do with this part, just to have three different blocks, right? But usually
Got it.
what you can also do, if you declare a variable inside here, it won't be accessible inside here. Like if you
Got
have
it.
an,
Like it's something like a global or local variable kind of thing.
yes. But I don't have a local variable inside here, but still I did this kind of thing because see, if I'm looking at this code, it looks much cleaner and it is visible to us that there are three different, like the same thing is done three times.
Got it.
So let's go to the next problem. So in this problem, we are given that Keksik keeps getting left on seen by Anji, and through a mutual friend, he's figured out that Anji's really likes binary trees and decided to solve her problem in order to get her attention. Now, Anji has given Keksik a binary tree with n vertices, where vertex 1 is the root and that does not have any parent. All other vertices have exactly one parent, and each vertex can have up to two children. So that is the left child and the right child. Now for each vertex, Anji has Keksik index of both. Anji tells Keksik index of both its left and its right child, or tells him that they do not exist. Now additionally, each of the vertices have a letter Si on it, which is either U, L, or R. Now if it is U, it means that if on the vertex U it's like written U, then if from that vertex you'll have to move to the parent vertex. If it is L, from that vertex, Keksik needs to move to the left child. Otherwise, if it's R, he needs to move to the right child. So now before his journey starts, he can perform the following operations. Choose any node and replace the character written on it with another one. So now you're interested in the minimal number of operations that he needs to do before this journey, such that when he starts the journey, he will always reach a leaf at some point. Like it's not required that he will stay at that leaf, or like he should end at that leaf. He should just be at some point on a leaf, and a leaf is nothing but a vertex which has no child. So let me first explain the problem here. See, a binary tree is given like this. So in this is a binary tree. Like each vertex is having at most two vertices, and the root node is not having any parent. So in this, what is given to us? Like something is written on this node, something is written on this node, something is written on this node. So what we have to do, see, these three are the leaf nodes. So if Kiksik starts from root node, see, first of all, he will have to change this. Why? Because he wants to go either to the left or to the right. So let's suppose he changed this to R. So if he changed this to the R, this is one operation, and then he'll end up here. From here, it is written R, so he'll end up here, R. So after some point, he'll end up here. That is a leaf node. So this way, he requires one operation. Otherwise, if let's say we made this instead of R, we made it L. So he'll come here, and then this U also needs to be changed to, this U will have to be changed to, let's suppose this is the left child, L. Maybe write this down a little like this. So this is a leaf node. We'll have to change this also to L so that kexic ends here, and the minimum number of operations like this is 2. So the minimum of this is 1. So this is our answer. Why we need to change this to L? Because if we don't change this to L, if we change this, like if this remains unchanged, from here kexic will go back. So he will just keep on circling in this, in these two, between these two vertices, and he'll never reach this leaf vertex. So the problem is, first of all, the problem is clear, right?
Yes, clear.
Okay, now how to solve this? See, this is a very simple, like something like if you are given, like if you are doing BFS and trying to find, see, initially, let's say these values are infinite and these values are 0. So what we can do, we can start from these, and each time, see, we'll try to get the minimum value of this node. So what we can do, see, from this vertex, let's say there is a left parent. See, left means L of I will give me left child of ith node. R of I will give me right child of ith node. If there is no right child of ith node, then this will simply be 0. This is given to us in the input. I'm saying I'll make another array LP, or let's say LL. LL is nothing but if I, LL of I is nothing but if ith node was left child of any node. Let's say if this is some j, so this means Lj was equals to I. This simply means LL of I is giving me if ith node is some left child of some node, what is that node? Basically, what is the parent of, like you actually don't need to do it like this. Like you can simply have a parent array also, because a node will have at max one parent. So you can have parent of I, and you can simply like you can, let's say this is j. So later on, you can just check if L of j is equals to P of I. This simply means that, what does this mean? L of j is equals to I. What does this mean? That the ith node was left child of its parent, right? If P of I is j, if the parent is j and left child of j is I, then this means that the left child of parent j is I. Left child of parent, left child of jth node is I. So I am saying, instead of having this parent array, you can also have something like LL of I is this vertex, right? Right now I is this vertex. LL of I is j. This simply means that this ith vertex was left child of j. Otherwise, if RR of I is j, this means this ith vertex was right child of j. Is it clear? This just having the reverse. Li is giving me what is the left child of I. LL of I will give me if I is the left child of this jth node. RR of I will give me if I is the right child of j. If RR of I is 0, then simply it means that ith child is not right child of any node. Is it clear?
Yes, it's clear.
Now using this, can I not do something like this? See, if this is the currently, this is the ith node. So I already know if this is the left child, I simply know how can I find the answer for this. Let's have a value calculated for each node. Value for this node is 0 because it's a leaf node. Like value is nothing but the number of, if I am like how many operations from this node I have to do to reach the leaf node. Like how many characters do I need to change? How many characters on these vertices do I need to change? And value for this is infinite. So value for this jth node is can simply be written as minimum of value of j or value of I plus 1. Why plus 1? Because if string at j is not equals to left, I'll have to change this, right?
Yes.
I'll have to change this. So this will be plus s if this is not L. So add 1, otherwise 0 if s of j is already equals to L, right? So this way I can backtrack and I can calculate the minimum value of this node. And this is my answer, right? I'm starting from this node. Is it clear? Minimum number of characters that need to be changed to reach these vertices. Is it clear?
Yes.
Okay, so let me show you the implementation. So this is like kind of digextras only. See, first of all, this is the left child and right child for each node. Then I'm having this LL. Like if the ith node is some left child of some node, what is that node? If RR of I is some value, then this is simply that. If the ith node is right child of some node, what is that node? So I'm going from 0 to n. If Li is equals to 0 and Ri is equals to 0, what does this mean? That this is a leaf node, right?
Leaf node.
This is a leaf node. If this is a leaf node, the answer for this is 0. Like you don't have to do any operation. Otherwise, right now, I take some bigger value, like very big value, 1e9, 10 to the power 9. Now, if ith node is having a left child, so by the way, these values are given to me as one index. So that's why I'm just doing a -1 here. So if left child is there, so for LL for that node, the parent is I. And if R, there is a right child of ith node, then for that node, this is that node. If I start from 0. And ith is the parent of that node. Now I'm doing a simple, like I'm inserting everything, like in register, we insert everything in priority queue, right? Yes, no.
Yes.
So I'm inserting everything in set, and then I'm just doing, I'm picking one of the smallest value nodes. And from that, what I'm doing, if X is more than answer of I, that is, like I'm just skipping this, like there's a better answer for this node. Otherwise, if left, like this ith node is some left child of some, if this is like true, LL of I is not equal to mentioned, this simply means that the ith node is left child of some node. So for that node, if the answer is more than X plus, for that node, if the character is not equal to L, I'm adding 1. Otherwise, I'm not adding 1. So I'll update the answer. I'll insert this new pair in my set. Otherwise, if the ith node is right child of some node, for that node also, I'm updating the same thing. Finally, my answer is 0. Answer of 0. Is it clear? Like I have complicated it slightly using this LL.
Can you actually explain the that LL and RR part in the while
LL,
loop?
okay, in this part.
Yeah.
So if currently I'm at ith node, LL of I is nothing but if ith node is left child of some node, what is that node? So we are going up in the tree. We are starting from leaf node and we are going up in the tree. If this is the left child of this node, so LL of this I node will give me this node. So for this node, I can calculate answer accordingly. So there are, by the way, there are only two cases. Like we can do it directly also, but like you don't have to use multi-set or set. We can do directly also. But what I have done, so best of these two, right? Like whatever the answer was. So what I have done for calculating from this to calculating answer, let's say the answer for this is X. So what I can do for calculating the answer of this will be X plus 1 in case the character on character on this node, let's call this as J. If on this node the character is not equals to L, right? You'll have to change the character here. If this is not equals to L, otherwise it is 0. If S of J is equals to L, right? Yes, no. If the answer for this node is X, we can calculate answer for this node will be minimum of these two. This one and X, let's call this as X dash. If the value for this node is X dash plus 1 if S of J is not equals to R, and 0 if S of J is equals to R. Is it clear now?
Can you
Yes, it's
repeat the implementation set part only?
Okay, set part set, like we don't actually have to use set, but set is used to just pick the smallest currently. Like if we are here, let's say the number of operations required for this node is 2 and for this node it's 5. So we should update this node according to this 2 value, which is smaller, not according to 5. So that's why set is used. First, pick the smaller values to update.
Can you
Later
just
on,
like repeat the while loop? I didn't understand the while loop. I understand the concept, but the implementation
okay,
of it.
first choose the smallest node which is having the smallest value, then erase it from set. If this value is already not equals to answer of I, that means we have already computed, like we have a better answer for I, then simply continue. Otherwise, we'll update. If this current node is left child of its parent node, update the parent node. If the current node is right child of its parent node, update the parent node. Is it clear?
Yes.
Okay. So this is clear to everyone, right?
Yes, yes.
Okay, so let's go to the next problem. So in this problem, we are given that let A, B, C be integers. We define f, A, B, C as follows. Order the numbers A, B, C in a way such that A is less than B, B is less than C. Then return GCD of AB, where GCD AB denotes the greatest common divisor of integers A and B. So we just take the two smaller values and ignore the bigger one. So we have to calculate this value. Like for every I between 1 to n, for every j between I plus 1 to n, and for every k from j plus 1 to n, what is f of, like what is the sum of this? F of ai, aj, ak. So let's suppose the array was initially sorted only. Let's say we have a sorted array. Okay? So there are these values and we have to calculate this is what we have to calculate, right? So let's say if I already know, like for ai and aj, I'll try to see that how many values are, like we can do this anyway. See, either my GCD depends on only these two, right? AI and AJ. If I have already sorted, AI will be less than equals to AJ, AJ will be less than equals to AK. So my GCD only depends on AI and AJ, right? Yes, no.
Yes.
Okay. So if my GCD only depends on AI and AJ, so let's suppose currently my AJ is here. So all the values that appear after this are valid option for AK, right? Yes, no. Like
Yes.
anything can be AK. It doesn't matter. The only if I have AI and AJ decided, then GCD is decided. So let's say let's call that as GCD. So my answer will be GCD into the, let's call these are the remaining number of values in this part. Array A is already sorted into remaining. For this AI and AJ, right? Because AK can be anything. AK can be this thing, AK can be this thing, AK can be this thing. The value will be GCD. This value won't change. Now, the thing is, if let's say AJ is decided, what can be the GCD of this thing? The GCD of AI and AJ can be something which is divisor of AJ, right?
Yes.
So let's say we already have found all the divisors. We know, like how, first of all, we can also find the divisors in square root time, right? But let's say we have already computed, we know divisors of this. So what we can do, we can have, let's say we can iterate over those divisors. Let's call those as D. And we just have to count how many of those are first time dividing, like how many of those, if let's say we have something like count of D is nothing but this will give us how many values, how many values, how many AIs such that I is less than J are divisible by what? D. If we have this thing, we can simply add to our answer for every D, which is divisor of this, into remaining. There is only one catch right now, but first of all, is this making sense? Like all of these can be potential. If I take these values, any of these with A, J, I will get my GCD as D, right? Yes, no.
Can you repeat this again?
Count D is how many, like count of AI such that I is less, basically in the prefix of J, how many are divisible by D? How many values are divisible by D for the first time? Like forget about for the first time. If they are divisible by D, D can be GCD of AI and AJ, right?
Yes.
Right. But the thing is, if we do something like this, let's suppose the array was 2, 3, 6, and 12. So if let's say we are taking 6 as our like let's say there is a value which is having 2, 3, and 6 as its divisor. Let's suppose 6 is the value itself in some prefix. So we cannot say that for like D is basically a divide, like D is some divisor only, right? So we cannot add this count D directly, like count D, like 2 also divides 6, 3 also divides 6, 6 also divides 6. But we cannot say like if let's say like 2 is also GCD, if let's say 6 and 12 are the numbers, right? So 12 will have like what all pairs will 12 have as divisor? 1, 2, 3, 4, 6, and 12. So if I iterate for all of this, and is there any number, let's say this is 6, 12, and there are some numbers, and the divisors for 12 are 1, 2, 3, 4, 6, and 12. So if I, first of all, is there any number which is divisible by 12? How many numbers are divisible by 12 in this part? No number, right?
Yes.
So this will add 0 into remaining. Let's say remaining numbers are 3, 1, 2, 3. Then how many numbers are divisible by 6? In prefix of this. No, not including 12, before 12, like in prefix.
1.
This is my J. How many numbers are divisible by 6? 1. So this means that 6 can be GCD once, like if I have one option for AI, for which if I choose AI and AJ, I will get GCD as 6 and the remaining is 3 only. Like AK can be anything. But for 4, it's also 0 into 3. But for 3, again, you will see that there is one number which divides 6, right?
Yes.
So I cannot do 1 into 3 here. Why? If I do 1 into 3, this simply means because this, for this I have already included my GCD as 6, right? For 2 and 3, because 2 and 3 again divide 6. So for these, what I can do, once you are getting some number, this thing, these are the valid operations, right? For all of the divisors of 6, for all of these numbers, once you're getting these values, you can subtract these values from the divisors of these. Like this is kind of DP. So you'll have to decrease these values from the divisors of 6 so that you don't like do multiple computations. Like you don't include these values multiple times. Let me write this again. Try to understand. So divisors of 12 are 1, 2, 3, 4, 6, and 12. How many numbers in this part are divisible by 12? 0 into 12. How many numbers are divisible by 6 in this part? 1 into 12. 1 into 3. Like 3 is the remaining value. So I have these many options, 1 into 3. Now what you'll have to do for this one, you'll have to subtract this one from these, like count of these. Why? Because later on you'll see that 3 also divides this thing and 2 also divides this thing. So you'll have to do a minus 1 here. For this, it will be 0 into 3. For this, it will be 1 value because 1 divides this, but you have already -1 because you have already computed it. You have already taken according, like GCD for that.
Yeah.
And for this also 1 -1. So let me take a more complex example, then it will be much more clear. Let's take this thing which is given to us in the input. Okay. So we have so this is it, and 5. Okay, there are 5 numbers: 2, 3, 6, 12, and 17. So this is already sorted. Now for this there is no number in, so I'm skipping this. Now this is the number j. So what are the divisors for 3? 1 and 3. How many divisors of 3 are in this part? No. How many divisors of 1 are there? How many numbers are divisible by 1? 1. And what is the remaining numbers in this part? 3. So if this is my j, I have one valid option for ai, and this is also needs to be multiplied. Why? This is the number of options and this is the GCD. This is the number of valid options for ai, valid options for ai. And this is valid options.
And that valid options are in the prefix, right?
Yes, yes, yes. Because ai is first, then it is aj, and then it is ak. And my GCD only depends on these two. Therefore, for AK, I'm taking all the valid remaining options, valid options for AK.
Okay, okay.
So let's do this for all the values. So this is this value. Then for 6, what are the divisors of 6? Divisors of 6 are 1, 2, 3, and 6. How many values are divisible by 6 in this part? Nothing. So
0.
6 cannot be my GCD. How many options values are divisible by 3 in this part?
1.
1. So the value for this will be 1. There is one option. The GCD is 3 right now. The value is 1. And how many options are left? 2 for
2.
AK, right? For 2. How many values are divisible? For 3, I'll also have to do one thing. For all the divisors of 3, I'll have to decrease it by 1. But right now there is no divisor of 3 in this prefix, so I'm not doing it. Okay. But I'll show you that for 12 when I reach 12. Now for 2, how many values are divisible by 2 in this part?
1.
1. So there is one possible option for AI such that my GCD is 2, and how many remaining options for AK? 2.
2.
Now let's start for 12. So these are my values up till now. These are my valid answers. Like everything will get added to answer. Now for 12, what are the divisors? For divisors
12,
are
1, 2, 3,
4,
6,
and 12.
1.
So how many values are divisible by 12? Nothing, right?
Yep.
In this prefix, how many? Nothing. So
0.
0. For 6, how many? One value is divisible. The GCD will be 6, and
Remaining will 2, 1. Remaining is 1, right?
yes, remaining is 1. Now this is one option. Like you'll have to decrease this one option from divisors of 6, which is 3 and 2. Okay.
Okay, got it.
Why? Because 2 and 3 also, like 2 and 3 have also, like you'll also include the divisors of 2 and 3, but those already have GCD as 6. So this is like GCD is greatest common divisor, not just divisor, right? So this
Yeah,
is 6. This is greatest common. So for 6, this 6, you won't include 2 and 3. Now coming to 4, 4 divides nothing, right? In 2, 3, 6, among 2, 3, 6. So this is 0. Now 3 divides how many numbers? 2 numbers, right? 3 and 6. But 6 has already been gone. That's why -1. So 2 minus 1 is 1, right? There's a -1. 3. How many numbers 3 divides in this part?
2.
2. But -1 gives us 1, right?
Yep.
1. GCD is 3. Remaining is 1. Again, for 2, how many numbers divide? 2 divides in this part? 2, right?
Yeah.
And I think I skipped 1 here. So I'll calculate it in a moment. But 2 is -1. Like 2 divides 2 numbers. -1 is 1. GCD is 2. And
Remaining is 1.
remaining is 1. How many numbers 1 divides? Actually, for all of these, what will happen?
3.
6, 3. But for 6 also it's -1. For 3 also it's -1. For 2 also it's -1. Right?
Yeah.
Because all the divisors of 2, I'll do -1. For all the divisors of 3, I'll do -1 because this is the value, this I'm doing -1. And here also. So that's why 0. And here also, in this part, how many numbers are divisible by 1? So first I'll have to remove all the divisors of 3. 3 was 1, so -1, and 2 also for -1. So here also 0 for 2, 1 now, right?
Yes.
And for 17, I don't have to check because the remaining is 0 after this. There is no valid option for.
Yes, yes, yes.
So now let's find the sum of all of these values. So 1 into 1 into 3, 3, plus 2 into 2, 2 into 1 into 2, 4, plus 3 into 2, 6, plus 2 into 1 into 1, plus 2, plus 3 into 1 into 1, plus 3, plus 6 into 1 into 1, plus 6. This is the value, right? I didn't
Yes.
skip. Okay, so let's find the sum. 3 plus 4, 7, 7 plus 6, 13, 13 plus 2, 15, 15 plus 3, 18, 18 plus 6, 24. What is the answer? So we are getting 24. So
24.
So the answer is 24. So now the idea is clear, right?
Yeah, the idea is clear.
Okay. So now we just have to use pre-computation and implement this. So let me show this via code only. So see, since the values are between 1, like the array values will be between 1 and 10 to the power 5, I'm just pre-computing all the divisors using sieve only. And I'm sorting them in non-decreasing, like non-increasing order, so that it will be helpful for me later on when I'm decreasing these values. Then I'm using these common, like global vectors. You can use map also. Like I'm clearing them down here. So it's like this is kind of just clearing it down. So you can use map also here. Then I'm taking array A as input. I'm sorting it. Why sorting it? Because so that I can just say that AI is this, AJ is this, and everything is remaining valid option for AK. So this is my answer. Initially, remaining will be n. So first, like I'll keep decreasing rem on each iteration. Now, like I said, count of D and okay, this current, I don't think this is used. For every divisor of E, this thing, count of D minus how many times I have already decreased something from this D. Like we were decreasing, right? And
what is actually count of D?
Count of D is how many times this D is divides some number in prefix of I, like how many valid
Yeah,
options.
got it.
And temp D is how many times I have already decreased a value from this. Like basically, let's say this is a -1, right? 2
Yeah,
divides how many numbers in this prefix? 2 numbers. So this is
2
count of
numbers.
D. Count of D. D here is 2. And temp of D will be temp of D. D is 2. Temp of D will be this thing.
Got it.
So instead of -1, temp of D will be 1. So that's why I'm subtracting it. So count of D minus temp of D will give me how many valid options are in prefix. Then, like I said, for each of these divisors, for all of the divisors for D, I'll have to increment this. You can also subtract it and then add it here, but just add it for later, right? If 6 is D, then for 2 and 3, you'll have to do this thing, right? 1, 2, and 3. Then
Yes,
the answer is nothing but D. D is nothing but the divisor itself. This is the GCD right now. This is the val. How many valid options for you have for AI and remaining. This is the valid options for AK. One LL is simply to have everything in long. Okay.
Yes, got it.
So this is GCD. D is GCD. Val is the valid options for AI. Rem is valid options for AK. This is just clearing my temp. Like since I have used a global vector, making everything 0. Right? And now I'm going for next iteration. So I'm increasing, like current value is divisible by all of these divisors. So I'm increasing this because now current E, like current will be previous, like current value is in prefix now for the future values, right? So I'm increasing count to D, where D is every divisor of E, current value, right?
Yeah.
And finally, since I'm using global, I have to make all of count to D is also 0. finally I can print my answer. Is it clear?
Yeah, it's clear.
Okay, so that's it, and thanks for joining. Bye bye.